Thank you, thank you. Good to see you all survive Wednesday night, and I hope you're all caffeinated. I know jet lag is one thing, but the inconsistent availability of coffee has been my bane here. So just a quick scheduling note. The slides are broken into 3 parts, but due to the truncated schedule with the bus changes, we'll be definitely covering the deep learning material during the first hands-on session this afternoon before the break. So if you wanted to specifically see that part of what we're covering here, then make sure you're there for that. This talk will cover big data. We're going to cover handling big data using a system called PySpark, and we'll briefly discuss clustering. And then in the hands-on session, we're going to do a few brief PySpark exercises and then immediately dive headfirst into machine learning and deep learning. So let's take a 1,000-mile overview of the journey ahead here. This journey is typically several semesters in the Masters of Data Science program at CMU, and we typically compress this down to a 1.5-day workshop. We've been doing this series for over 10 years now. We're going to squeeze it today into about 4 hours, so we'll see how much of it we can make work. I know that from talking to a bunch of you that you're all pretty bright, and we're going to be able to move at a decent pace here. So, but I will pause for questions periodically, and feel free to stop me at any point. We're going to get to building some interesting neural nets at the end of this process. And I just wanted to make one more note, which is that I'm going to be walking a fine line here. I do want to make sure that this makes sense to those of you who is introductory and still offer some perspectives to those of you with considerable experience. And in fact, from talking to a bunch of you, there's a good chance that a lot of you know more about it than I do, and that's completely fine. But I want to make sure that we get everyone up to the speed where we can all start doing things. And in fact, my goal is not so much to make you, to present you with the theory, but to present you with actionable ability to use PySpark and to use TensorFlow and to start wrangling your data and to start building neural networks. And so I want you to think not so much of me as your teacher, as your concierge, and getting you to the point where you can do some of this work. So we're starting here with our big data, and this fine person is climbing the mountain, finding that the big data lends itself naturally towards machine learning, and often the distance is AI, and we're going to talk about a little bit how we're going to get to there. So the topic today is big data, and we have to ask ourselves, what is big data? And Wikipedia's definition is a pretty good one. Big data is a broad term for data sets so large or complex that traditional data processing applications are inadequate. The goalposts are moving constantly. The price of storage is constantly changing. The amount and kinds of data that we're able to and willing to keep is constantly changing. But we are constantly able to do a certain amount of work on our laptops, and then we find there's some work that is just prohibitive for that, and we have to build up to perhaps a cluster. And then when those normal means fail, then we need to find even better ways. So we're going to dig into some of the ways that we can approach problems that are too big for our standard methods today. So, in the midst of history, we have grandma's recipe box back when there was only small data. Oop, wrong slide there. So, let's say that we want to find a tasty appetizer. That's easy. We rifle through, we find an appetizer, we're good. We want to find something to use up all the cherries, and I have a cherry tree, so I have this problem every June. So if you have a cherry recipe, by all means share it. But let's say that we need to rifle through the box, and it's going to take a while for one person to do it, so we convene a group of people to do it, and we try to do the operation in parallel. Maybe it goes a little faster. We spread all the recipes on the table. Sometimes our indexing schemes can be less sophisticated, and sometimes that's better. Maybe we have a pile of papers or of magazines or whatever, like in my office, where it's geographically organized, or your tax papers sometimes end up this way. Let's say we want to find all our articles from 2007. We just dig down in the pile. That's pretty easy. Let's say that we want to get all our papers on fault tolerance. Well, that's a little more difficult. We're going to have to start digging through the specific contents of each one. We can do some indexing, which can improve the individual performance, but teamwork, again, is always going to be the key to speeding that up and making it practical. And there was a time, when I was younger for sure, when that was the only real practical way to find anything of this sort. So our only hope really is to hire a group of researchers when we have a difficult problem like this. Let's say we want to find the books on modern physics. That's easy enough. They're at Dewey Decimal number 539. I know probably they don't even teach Dewey Decimal anymore, but that's how I learned it. Let's say we want to find all the books by Wheeler. Well, that's easy enough. We can go back to the card catalog and look up the indexes that we have there. They're pretty good. But let's find all the books where he isn't the first author. That's going to be a much more difficult proposition. And once again, our only hope is to hire a group of researchers who understand the material and have some familiarity with it and get deep into it, or at least that's how it used to be. But as time went on, data started to grow. We had to accommodate more of it. Here we have a picture of IBM Model 350, which was a 5 megabyte hard drive, bigger than a washing machine. It was expensive to store data, but you could store a lot more of it. So you had to think about what you wanted to save, and you wanted to organize it in a way that made it useful to you. So we would have some really significant heavyweight hierarchical systems in order to manage our stuff. And I wonder if there's a USB plug for that. I don't know. So finally, anyway, we get to bigger data. I do remember that when the consumer hard drive prices fell under $1 gigabyte, and I was just amazed. And now you can go to Amazon and for $130 get an 8 terabyte drive that you just plug right into your machine, and you have an incredible amount of storage. So storage got cheap, and we kind of shrugged our shoulders and said, why not keep it all? And in fact, data has become a hot commodity. We keep so much more of it, and we need new tools to wrangle it. And the new approach is just keep everything and monetize it and to capitalize on it. And somewhere along the way, someone came up with the idea that a Library of Congress would be a good yardstick or a good unit to measure data. And that was theorized to be at 10 terabytes, which was always a ridiculous and apocryphal number. But it's a reasonable number still. 10 terabytes is an amount of data that you usually have to think a little bit about. You don't just shove it from one place to another without thinking about whether there's enough space and how long it will take, et cetera. The time will probably come when that becomes a trivial amount, but still it's a decent starting point. I think we could say that 10 terabytes starts to approach the level of big data. Size isn't the only factor that we have to consider when we think about big data, though. There's the 3 V's of big data, which are volume, velocity, and variety. Volume, of course, size. We've got data sets that themselves have hundreds of terabytes, possibly even more. We host a few of those on Bridges 2 ourselves. We've got the expectation that we're going to have this incredible fire hose of data coming out of the square kilometer array. They're expecting to have an exabyte of raw data every day, which will be compressed down to 10 petabytes. Which poses some real challenges for our ability to store it, even with the increased modern ability to store data. And then we've got things like the GDELT, or the Global Database of Events, Language, and Tone, which has become a broad sort of big data, where the initial categories were fairly simple, and it's grown a great deal over time, and we need special tools in order to handle that. So it used to be that we would just decide if we were going to keep our data, we were going to put it into an SQL database, we put it into an RDBMS, something like Oracle, something like MySQL, et cetera. But in recent years, as our data sets have grown and our needs for them have grown, there's been a movement to create something called a NoSQL. Because we want to find something that's a little more flexible, but can still do all of the storage that we require and provide the tools to handle that data. So modern approaches require more flexibility. Queries require maintaining complicated indexing schemes, but maybe not as complicated as we might have in an SQL database. Another problem with the old school SQL databases is that sharding and scaling is a big problem. It becomes really difficult to have single points of failure at the top of these collections of data through which every request has to pass. And finally, there's these guarantees that impose costs, and this is a big one. They're called asset guarantees. You've probably heard these words if you work in this field, but if you haven't, it's atomicity, which guarantees each transaction is treated as a single unit that succeeds or fails completely. Consistency, which ensures that a transaction only brings the database from one valid state to another. Basically, everything has to follow the rules all the time. Isolation, so that even if transactions are executed concurrently, that they leave the database in the same state they would have been obtained if the transactions were executed sequentially. And finally, durability, which guarantees that once a transaction is committed, it will remain committed even in the case of a system failure, for example, a power outage or a crash. And this usually means that completed transactions or their effects are recorded in non-volatile memory. So, if you have a few million yen in your pocket and you deposit it in an ATM here before you head home, you do want to make sure that that actually makes it into your bank account and you don't have the, the effects of a a summer storm or the monsoon season affecting your ability to keep that data in your bank. However, those guarantees are very useful for things where we have to keep track of every little bit and every moment. But when we want to have access to extremely large collections of data where we might not even know what's in it, and we certainly don't have a careful, pre-thought-out, hierarchical organization of our data, like a ledger would have, then these rules become more of a handicap than a hindrance than a help. So basically, we surrendered. We gave up and we started to use various different kinds of key-value pair systems. And I'm going to talk about a few of the different ways that we've tried to replace databases. Sometimes less is more, because key-value pairs are perfect for big data in that we can reason about them. But we're not locked into a heavyweight RDBMS guarantee. But as we'll see, we can add the bits that we want back in to a greater or lesser extent. And we defer the work of assembling our data. And we find that we reap some big benefits with scaling when we do that. The keys and values can include as much or as little structure as we want them to, and we put them all back together as needed. And I like to think it's a little bit like IKEA furniture. It's cheaper to ship and store it if we don't put it together until we take it home. There might be some swearing, but we didn't have to rent a truck, so we win. So, how does a pile of unorganized data solve our problems? Our hypothetical squad of librarians has been replaced by parallel computing, and we can afford to defer organizing our data because we have an infinitely large team of searchers to scour that data now, so we don't have to worry as much about a hierarchy to give humans hints about where they might find something. This is what they look like today. So some examples of ways that the approaches have bucked the SQL trend. We have document databases like Cassandra and CouchDB that offer some guarantees about formatting of the data with different approaches and different levels of performance. But the common theme there is that the structures are more flexible. Wide column stores are also an option, and they, to some extent, have tried to recreate some of the advantages of SQL with, while still preserving some of the benefits of scaling with less structured databases overall. It's not hard to see that you can get most of those benefits without the full cost of a framework. Each column store is implemented a little differently, but they're all designed to scale horizontally to a very great degree with minimal performance cost. It's somewhat of a hybrid approach. And then there's graph databases, which primarily map relationships like the old 6 Degrees of Kevin Bacon game. Common real-world problems dealt with by special database systems sometimes are well represented in these kinds of databases, but they can also be hard to visualize. Serialization of them can be difficult, and queries can become really complicated. I'm not going to go into a lot of detail here, but if you're interested in graph databases and the systems that provide them, Sparkle and Cypher are two that have a lot of advantages. And I'm going to try to keep moving so that we keep on track for this afternoon. So there's also the graph databases are not curiosities, but they are behind some of the most high-profile pieces of the web, and they're definitely big data, and there's a few examples. So we have to ask ourselves, we used to include Hadoop in our big data presentations because at the time that was an emerging favorite to do these things, and then Spark. And Hadoop and Spark are similar, and you have to ask yourself, what kind of database are they? The answer is they are not. They are not databases at all. They are data frameworks. Spark and Hadoop exist in a middle space as a programming framework, a set of binary clients, a collection of infrastructure servers, and an ecosystem for application development. We're portraying Hadoop here as sort of the Stonehenge of big data, and we salute it, but its time has sort of come and gone. And if you live long enough, you too will become an expert in a completely obsolete technology. The core insight of both these systems was to bring the computation to the data. We're bringing the computation to the data so that we can not have to move the data as much just to get started with our process, and we gain big scaling advantages by doing so. When I started at PSC, we had a machine which was called Lemieux, which topped some charts back in its day. And Lemieux had a small file system available for computation. So one of my first tasks was to set up testing for a caching system we used that would queue and shovel data in as fast as possible. We were bringing the data to the computation because at the time, computation was very expensive, and storage was, storage was the ability of that to access all the storage was relatively limited. So in 2006, Google released a paper that described their big table MapReduce system, which inspired the creation of Hadoop, and that later led to the creation of Spark. The paradigm was that the computation would happen in parallel on the host that stored the data and then be aggregated afterwards. For embarrassingly, or as some say pleasingly, parallel tasks, this was a really big win. Now, Spark has added in a lot more very useful bits of framework, whereas MapReduce was the only way that you could really use Hadoop. So Spark has created an SQL format. It's added in data frames. It's added in a lot of user-friendly methods for accessing your data. But we're going to talk about using Spark with RDDs today, and I'm going to get into what that means shortly. So the Hadoop model was to use a MapReduce model, and it's not a bad one. And in fact, you'll find a lot of your workflows end up sort of naturally falling into this pattern. This was the only way to use Hadoop at the start, and there was always the promise around the corner that they would make it easier to do other things, but really people kept trying to shoehorn whatever kind of problem they had into this format. But it is a quite useful one. You'd start with your big data that comes from multiple sources and multiple places, and you apply a map function to it. You convert all of it into a more usable format, and then you aggregate it using a reduce function. And then you possibly do another round of that and reduce it, and then you get your answer. So for example, let's say we want to find any big swings in the Bering Sea surface temperature. The data comes as a series of timestamp temps for each transponder. Here we see the transporter ID and the coordinates. And we decide we're only going to keep the ones for the Bering Sea, so we filter some of them out. And then we want to find the biggest change at each transponder in the last 24 hours, and here we go. We have our answer. So Hadoop has come and gone for the most part, although there are certainly some installations still, but some of its ecosystem lives on. So I have been surprised how often I see Zookeeper come up, which does some orchestration and configuration for various projects. The HDFS distributed file system had a lot of really interesting advantages. It lived on top of other file systems and could be used as a standalone back end. It had read write once, read many, or worm performance, which made streaming really fast, had rack-aware redundancy. And these things were all really useful, but ultimately the limitations of the programming framework caused Hadoop to kind of fall behind the wayside. But you'll still see some of these things out and about, Yarn, Spark for sure, and some of these other projects, a lot of the Apache ecosystem. So HDFS is still used, but arguably no longer a good choice as a backend for Spark. But Spark has some big advantages over Hadoop. So the first one is performance. So from the very start, and this was in the pretty early days of Hadoop, Hadoop was initially started as a way to take advantage of the very large collections of disk that were available on these nodes that held them, and to do the compute locally. But these nodes typically, since they were just for storage, didn't really bother with a lot of memory. As time went on, memory got cheaper, and more memory was installed in the nodes that actually held the storage. And Spark came along and decided we're going to keep all of our data set to the greatest extent possible in RAM, and that's going to be our focus. And it worked really well. Turned out to be a big advantage over even the already pretty impressive performance of handling very large data sets that Hadoop had. Also, they decided to be smarter and to use a directed graph system internally so that they could reorder some operations and make things work a little bit better even than you had intended, and to really abstract a lot of the difficult parts of handling very large data sets out away from the user. They also had a big edge on ease of use because Python, Scala, and Java all were and still are first-class citizen languages. So you can do basically everything. All the libraries tend to be written and well documented for each of those languages, which turns out to be a big win when we try to do our machine learning work later. And finally, some new paradigms emerged, like Spark SQL, streaming for catching the fire hose of data that's coming at you, the machine learning libraries, GraphX if you want to do graph database work, and some others. Once again, though, well, I guess I should reorder that. Okay, so this is kind of the same idea, but improved. Spark uses a driver program that distributes work and data to the other nodes in a cluster. And this is meant to be transparent to the user. So while there's some parameters you can tweak or that an administrator could set for you, it's really not meant to require direct node management like you might have to do in other kinds of parallel programming. Even when that's abstracted out, you're still sort of telling different nodes to do different things, but to a large extent, Spark is designed to really let you work with an incredibly large cluster as if it was just one single machine. It's meant to abstract away all those implementation details and make you work with giant data sets and do pretty useful things in surprising amounts of time. So I could actually give an entire talk about the deployment details for Spark clusters and the configuration options, but good news, my job here is actually to go back home and also here to save you from having to ever think about those things. Really, you want to do the work that is relevant to your science and not have to think a lot about how the cluster is configured. If you get to that point, then you might be at the point where you have to think about whether it's really suiting your needs. So. The Spark formula, how does it work? We've broken out of the rigid MapReduce framework that we had with Hadoop, but there's still a general workflow that looks kind of similar. We start with, we create and load an RDD, or a resilient distributed data set. So for instance, web page visitor IP address logs. We collect them and store them in various places in our cluster. We do transformations on our RDD. So for instance, we might filter out all non-US IPs, but don't do anything yet. So we wait until the data is actually needed, and perhaps we do a whole bunch of transformations on our data that do not actually do any computation yet. We're basically sort of creating a plan prior to actually digging in and incurring the cost of actually doing any computation. So maybe we apply some more transformations like distinct IPs, et cetera. And then finally, we perform actions that return data. And this is an important part of the paradigm here. So maybe we ask how many unique United States visitors. We'll talk a little bit more about transformations and actions shortly. So I just wanted to show you a simple example. There's no need to follow along here, but we're going to do some similar things during the hands-on section. In this short example, we're working in the PySpark shell. So all of our work today will be done using Python in PySpark, but we're not going to get fancy. We're not going to use decorators or anything even remotely complicated. We're going to try to stay true to Python as readable pseudocode. So in this case, we're assigning lines RDD would be equal to sc.text file, and we're handing it a file which is tab separated values that includes server logs from a NASA project. And SC stands for Spark Context. That is the daemon that will be holding, or rather the object that will be holding all the information about Spark inside of your Python shell. Text file is the input function that pulls in the data from any text file and stores that in a key value pair. There are other methods of input, and I'm going to talk about that a little, but we're not going to go into a lot of detail. That's beyond the scope of what we're going to talk about today. You might want to refer back to parts of this slide here later. We include some information about how you would run in a batch job, for instance. The SC is provided for you when you use the PySpark binary, which gives you an interactive Python shell. If you're working in a Python script, though, you have to establish the SC, or Spark context, yourself. And it's just done with these couple of boilerplate lines, and then you're good to go. And then you would run Spark submit in order to actually run the code. Okay, so here we filter for some lines in our input that have the word Hubble, and then we count them. And as a sanity check, we take the first record that matched and we verify. So here we have the lines RDD line, and then we're going to create a new RDD. And remember, transformations convert one RDD to another RDD, but they don't do the work yet. So we're going to do linesRDD.filter, and I'll go through a list of these functions that are available. We're going to filter according to this function on the left, and then this is what's returned. So this is a lambda. If you're not familiar, this is an anonymous function. It's just a function that's so simple it doesn't need a name, effectively. So we take line as our argument, and we check to see if Hubble is in the line. And the answer is the answer is an RDD, and that's just returned silently. And then that we check the number that are in that, and this is actually an action, and we turn out to have 47 entries that match. Okay, and then we're going to do a first command, which lets us take a peek at our data, and we're going to make sure that everything appears to be sane, and we're reading the file we think we're reading, et cetera. Okay, so we filtered out Hubble, and we've talked about lambdas, and these are not unique to Python, but if you're not familiar, again, they're just anonymous functions. So we're going to see quite a few of these in our very simple examples. Okay, let's talk about some of the transformations that you can do. And again, these are the things that we're going to do in order to sort of filter and prepare or even clean our data before we try to do anything serious with it. So there's a map function, which is very much like map from MapReduce. We're going to apply a function to each element that is in the RDD that we have, each key value pair. And the RDD that we're going to get back is going to be typically the same size because we're applying a function and getting an answer. And the goal is not to reduce them, it's just to change them in some way. And then there's the filter function, which is what you do when you want to filter. I mean, it's exactly what it sounds like. And when you want to end up with fewer elements, that's often what you're going to want if you're going to narrow it down so that you can work on a more reasonable data set. There's also flat map, which is similar to map, but it can do things like generate sequences and allows us to flatten out nested entries, et cetera. You pass a function on that can expand the contents, and you can end up with even more elements than you started with in the RDD that's returned. And then there's some others here. I'm not going to go into a lot of detail, but they work similarly to things in other languages like distinct, which will give you only unique entries back, and then sample, which lets you get a subset of it, and then some union, intersection, sort of SQL style commands here. Let's talk about actions too, though. So the actions are going to differ from transformations in that they actually go and operate on the data. So collect is the most simple one. That just returns the entire RDD and lets you do whatever you want with it. Count will give you the number of elements. That's pretty obvious. Count by value lets you identify distinct values and count the number of those. Reduce by a function. This one is sort of interesting. So it's a way of aggregating the data that you have, and the function needs to be cumulative and associative. So, for instance, you should be able to group any of the inputs in any way and still come out with the same answer. So you may remember addition and multiplication can work that way, but division and subtraction don't. So first and take, these are ways of peeking at our data, so we can return a certain number of elements. It's a good way to sanity check what you're doing without incurring a great cost on looking at the entire, or doing something with the entire data set. Top returns the highest value to elements. Take sample is just what it sounds like. Save as text file is worth mentioning just because it's one of the few ways to get direct output from Spark rather than having to resort to doing something on your, passing stuff in and doing functions within Python. And that allows you to export your results in useful ways. And for each is used mainly. We don't typically want to iterate on things in RDD, and this is an important insight. You typically want to do operations on everything at the same time and not step by step, but the for each function is designed to be able to be used for side effects, for instance, updating accumulators, et cetera, and is a little bit like a type of reduce operation. And you have to be mindful of the cost of doing those things whenever you actually do them, because on a very large data set, they can take some time. So, once again, transformations versus actions. Transformations go from one RDD to another, and their action is deferred. Actions bring back some data from the RDD. And the transactions are where the Spark machinery does its magic with lazy evaluation and clever directed graph algorithms to minimize communication and parallelize processing. So you want to keep your data in the RDDs as much as possible. Actions are mostly used either at the end of the analysis when the data has been distilled down, like collect, or along the way to, again, to peek at the process, like count and take. There are a few special functions in PySpark and in Spark that work with pair RDDs. So an RDD is a key value pair, but it does not necessarily have to have a value. It can be just a key. But if you have pair RDDs, which are collections of keys and values, then we can do some special things. So it's often a very efficient schema. We mentioned this in our NoSQL. And the RDDs are treated within implementation dependently within Python as tuples. If you have an RDD who has all of those elements happen to be tuples of 2 items, it's a pair RDD, and then you can use these operations. So reduce by key. This obviously you don't have a value that's not going to do much good for you, but you can reduce these. You can reduce them by while sort of grouping them by key, which turns out to be very useful sometimes. Group by key will combine values that have the same key, and each one ends up with a list. Sort by key returns an RDD sorted by the key. Map values We can use a function to change the values, but not the key, and that could be useful sometimes. And then we can extract the keys and the values if that's what we want to do. And of course, all the regular transformations still work on pair RDDs. So as with transformations, all the regular actions available to pair RDDs, there are some additional ones that can take advantage of key value structure. So for instance, count by key, which counts the number of elements for each key, and that's often useful for aggregating information. And you can look up the values for the particular key and get those returned. So there's also some that work with collections of pairs. So if you have not just a pair, but a pair of pairs, then you can do a subtract by key operation. You can do joins, which turns out to be extraordinarily useful, and then various kinds of joins, left outer, right outer, and cogroup to join the data from two different RDDs by key. And these turn out to be, again, to reclaim some of that database operation methodology that we used to have, and doing it in a different way. Any database designer will tell you how useful they are, and here's a simple example of where we might want to use them. Here we have an RDD of our top purchasing customers for our store, and we parallelize, which is a way of putting data that we have in another format into the cluster in a parallel fashion, and we've got these three entries. So. Okay, so we've got these two different collections, and we perform a join on them. And one thing to keep in mind is that RDDs are a little bit lower level interface. Oh, sorry, that's the next one. I'm mixing up my slides here. Here we go. Okay, so when we collect it, we get the names and the addresses joined. So there we are. Okay, and if you're coming from data frames, joins are congruent with the merge functions. So if you've used those, you might have noticed that they can take some time, even with small data sets, and they don't necessarily scale as well as the join operations do. The RDD operations are a little bit lower level interface than data frames. If you're not familiar, don't worry, we'll talk about this in a minute. But they provide a little less convenience, but they provide a little more expressive power. They're a little easier sometimes to reason about. So at last, I wanted to talk very briefly about Spark anti-patterns. And again, this is it's not a complicated concept, but it is something that's easy to forget at times. That when you're dealing with big data, you want to avoid doing operations where you try to ingest all the data at once. So for loops, or a collect in the middle of an analysis, or large data structures. So if we're running a for loop over all the elements in our RDD and trying to load them into a Python list in our laptop and then apply some function that we have all ready to go for it, is this a good idea? If we're working with Grandma's recipe box, it's going to work just fine. But for 100 terabytes of common crawl data, you're going to need a bigger boat. So the tools that Spark provides allow you to work with very large collections of data in the most efficient way, but you do have to be careful to remember the goal is to marshal that army of researcher nodes that we have, and not to try to bring it all back and do it the way that you're used to. You want to use the tools that are specifically designed to do this kind of work. So who needs this Spark stuff? As we do our first spec exercises, you might think of several ways to accomplish these tasks that you already know, but we're learning how to leverage scalable techniques that work on our very big data, so shortly we will encounter problems that are considerable in size. When you leave this workshop, you'll know how to harness very large resources. One of the examples that we've come up with as a way of dealing with this is to doing things where we search the complete works of William Shakespeare. And doing that is a lot different than search the entire web, for instance, the Common Crawl data set. But the principles can be the same. You can use the same techniques on either one. So everywhere you see an RDD, realize that it's actually meant to represent a parallel data bank that could scale even into the petabytes, even if some of the examples that we try in the process of learning this don't have that level of data just for time constraints. So let's talk about optimizations. We said that one of the advantages of Spark is that we can control things for better performance, and there's a multitude of optimization, performance tuning, and programmatic features to enable control. We're going to quickly look at a couple of the most important here: persistence partitioning, parallelism, and performance. So the performance and debugging we're not going to give a lot of time to here because they're very configuration and application dependent, of course, and also you're going to find that there are some very useful tools within Spark, but some of them are a little bit hard to use on Bridges too, unless you set up X forwarding. They all have graphical interfaces and a website for the UI that gives you a lot of introspection and insight into your data set. But they are available for you. You can set them up when you're ready to use them, and they can be a big help in trying to figure out what exactly is happening with your data. The persistence is related to the way that the cluster stores all of this information and the way that it keeps a configurable level of copies of the information stored in memory in different places, and also that allows it to perform some optimization in terms of taking advantage of parallelism to work on data in different places. So if you've got one node that has A and B, one node that has B and C, you could have you can split them up in a way that's optimal so that they don't have to wait for the other one to be worked on. The partitioning and the parallel programming capabilities, we're going to get into those in a little more detail as we go here. So, another brief word just about the I/O formats. So Spark has an impressive and growing list of input-output formats that it supports, including text, CSV, SQL type, JSON, all of these. I don't need to read the list to you, but you know what I'm getting at. Again, we're going to just work with text file today, but the kind of data that you have available for your jobs, there's a very good chance that there's an adapter that works well with Spark to import it directly into an RDD and work with it with minimal fuss. So. There's a system called Spark Streaming, which addresses the need for streaming processing of data with an API that divides the data into batches and is processed as RDDs. It has fast recovery from failures and timeouts, load balancing, integration with your static data, and also integration with other components. And 15% of the global data sphere is currently in real-time data. So that number is growing quickly, and it's really something that is a big advantage of using Spark to handle very large collections here. A few words about data frames. They're another attempt to impose some structure on your data, and they're not necessary, but they do exist, and we don't want to discourage you from using them. They basically allow you to view your data in a tabular format, and they make some operations work a little bit differently than they do with RDDs. We found that, especially for training, that using RDDs as a starting point makes reasoning about the large data sets easier, and in some cases better performant. But by all means, if you decide to use PySpark and you want to try out data frames, you look into them and use them as they are useful for you. We'll talk just briefly about how we create them. You can convert, it turns out, trivially between data frames and RDDs. So anything that you can do with an RDD, you can do with a data frame and vice versa. But again, you may find that the performance is a little better in the RDD. You might find, in some cases, that the usability is a little better with data frames when you, for instance, have a collection of, of geographical data like this. So in a lot of places, they're going to make a little bit more sense, particularly where your data is a little more structured. And then sometimes data frames are limiting. Again, RDDs can be easier to reason about, and they provide a little bit more flexibility. It is easy to flip back and forth. One minor technicality you do have to keep in mind is that the returned object is actually a row type. You might not care, but if you want it to be a tuple, then there is a process for changing it to be exactly the way that just a standard RDD would be created. And that's that. So. Speaking of, we also got pandas and SciPy and some other systems. If you've used any of those, you might wonder why you wouldn't just use those, and the answer is simply that they just aren't built to scale the same way that Spark is. So an RDD could be terabytes in size, and the operations on these can marshal massive resources that just don't compare to what you can get on your laptop or even on a very beefy server. So this is a system designed to cope with mountains of data in a coherent way. Some other alternatives that are available, there's a system called Dask. I think we might have heard of it in the Python talk the other day. It's smaller and lighter weight compared to Spark, and it has, at least at the time that we put this, Okay. So Dask is lighter weight. Spark has a well-established ecosystem. It's well integrated with other Apache projects, and Dask is a component of a large Python ecosystem, which gives it other advantages. It's sort of designed to enhance other libraries like Pandas, NumPy, and scikit-learn, and that could have advantages for you. Spark is older, and it's maybe a little, at least it was a little better tested when we rewrote this slide. This may have been a year or two ago at this point, though, so maybe it's a little bit better tested, and we should possibly investigate it more. But at the time, Spark was kind of the old reliable. Spark data frames also have their own API and memory model, which is something that Dask doesn't have. And when it comes to machine learning, this is maybe where it really shines, because Spark has a really effective machine learning library that's easy to implement with Spark MapReduce style system, whereas Dask relies and interoperates with existing machine learning and data science libraries like scikit-learn and XGBoost, and they're maybe not designed to piece together quite so effectively. Also, Spark does not support multi-dimension array structures, but Dask has full functionality of the NumPy model, so that is definitely something in its favor. And finally, Spark can process graph models using the GraphX library, and Dask doesn't have, again, at the time of writing, didn't have any method built in to do that kind of stuff. So worth considering, but so far, Spark we have found to be more useful. So. All right, let's take a brief moment here to talk about clustering. So I'm going to segue here. This is ordinarily where we would stop and do some basic exercises with Spark and possibly talk about the recommender system. But we're going to, in the interest of time, skip that and jump straight ahead to starting to talk about the things that sort of segue into machine learning. Spark's machine learning libraries do particularly well, and finding and grouping your data is a fundamental operation for all machine learning type work. We're going to take a particular look at one algorithm as a starting point for thinking about what's really happening and what these algorithms can and cannot do well. So in this image, we've got some coins. They're grouped according to denomination and color. You could also potentially, well, mostly they are anyway, not necessarily clustered according to size, not necessarily clustered according to their monetary value if they're not actually US currency. We don't know. It doesn't really look like it. But we can problematize this in a bunch of different ways. So sorting coins can be intuitive, and you can group them in a bunch of different ways, but there's challenges to implement it in an efficient way. And you might think it's trivial, and in 2D cases it often can be, but it can get really tricky. You can have pictures like this one, like the spiral, where it's all interdependent, and you can't really draw a clear line between it. Then sometimes you'll get something like this, and we're going to see an example like this shortly, where we have these very disparate kinds of clusters, and you can kind of, intuitively see that there's some bunches there of little, black spots, etc. But how hard can it be to count those clusters? How many are here? It's very hard to say. Even if you take some time, it's questionable. So we're going to briefly look at an example that has 5,000 2D points. We want to figure out how many clusters there are at their centers. Just as an aside, this image is very interesting. Based on this one image, humans were considered to have 48 chromosomes for the first half of the 20th century, based on interpretation of that image. So our innate ability to detect clusters is not always foolproof either. So.